Okay, in this video, we're going to talk about functions of several variables. Where we have a function, it takes an ordered pair and it assigns you a real number. The domain would be a subset of R2, and the range would be the set of values that f takes on for the x values for the x, y values in the domain. Here's an example of a function of several variables. It's the wind chill factor, or the wind chill index. Whereas if you wanted to find, for example, the wind chill when the temperature is negative 10 Celsius and the speed of the wind is 30 degrees, it actually feels like negative 20 degrees. You have to be given a Celsius temperature, and you have to be given a speed of the wind, which is 30 miles per hour. And if you know those two things, they can tell you what the wind chill index is. So what would the wind chill index be at negative 25 Celsius and zero kilometers per hour? Well, at negative 25, it's here, but then zero, there is no zero. I guess this would be zero here. So this would be, the wind chill index would just be negative 25. The wind chill index at negative 10 V, what they're mentioning there is you've got negative 10, and they're telling you what V is. So what this is, this is actually a function of one variable, isn't it? This is a function of V. Whereas if C is fixed at negative 10, they're asking how does the wind chill index vary as the speed of the wind varies? Similarly over here, if you're fixing the wind speed at 30, then this would represent how the wind chill varies as the temperature, the Celsius temperature varies. So this is a function of just one variable as well. Here's how it works with functions of two variables. You have a domain that's a subset of the x, y plane, and for each x, y in that domain, you're assigning a real number z, or f of x, y. A nicer way to think of it is, think of the domain as a region, a subset of the x, y plane, and then in the x, y, 0, perhaps. And then at that point, you can assign a z value to it. That would be the height. That would be the value of z that puts you on some kind of surface here. So the function of two variables, it can be represented by a surface. For every x, y in the domain, the z value puts you on the surface. So here's some examples of some functions, of a graphical way to look at functions of two variables. This function right here, the domain would be all values of x, y in R2, because you can plug in anything you want into the function. And now this function, z equals 9 minus x squared minus y squared, if you think of it like this, you see this is a paraboloid that's been reflected across the xy plane, and it's moved up 9, so it would look kind of like this. The range would be z negative infinity to 9. So this would be a paraboloid then, right? Okay. This surface here represents this particular function. You might not know what it is at first, but if you square both sides, you can see that it's the upper half of a sphere. It's a hemisphere. So your xy value would be a point in the xy plane inside the circle x squared plus y squared is 9, and then the z value would put you on the hemisphere. See, so the surface can represent the function. Keep on going here. When you have a surface or a function of two variables, the contour map can be helpful, where you take these cross sections, these CAT scans, and you can superimpose those on the xy axis. It kind of gives you an idea of the shape. We'll look at some of those in just a minute. On the homework here, they're going to ask you just sketch the domain. Let's practice that first. The domain for this one, what's inside better be greater than 0. So that means that x squared plus 9y squared is less than 9, which actually turns out to be it's the area in the xy plane inside, but not on the ellipse, right? It does not include the points on the ellipse, because that would make this 0. Natural log of 0 is not defined. So that would be the domain would be the points inside that ellipse. This one right here, let's see, if you square both sides, you get this. So for this to be defined, x squared plus y squared has to be greater than 4, or equal to. So it's the area, it's the region outside this circle, right? Now the domain would include the circle itself, but it's everything else outside the circle as well. This one's kind of tricky. You have two issues. For this to be defined, x must be less than 2, and this cannot equal 0. So if x is to the left of 2, but not on this circle, x squared plus y squared is 1. So that would be the domain of that. Let's keep on going. Now they want you to sketch the graphs, now that we know how to do the domain. So remember, when you see f of x, y, think of z. Z equals x squared. It's a parabolic cylinder. The domain would be all of R2, and z, I believe, is greater than or equal to 0, right? This one looks like, if you look at it this way, I believe it's also going to be a paraboloid. The the domain would be R2, and then the range would be z less than or equal to 2. This one right here, it looks like a paraboloid that's been moved up 1 unit, doesn't it? Sure are a lot of paraboloids. It's because they're easy to graph. I think that's one of the reasons why we always look at them. Anyway, so the domain would be R2, and then the range here would be z greater than or equal to 1. See if you can match the function with the surface. Hit the pause button. Okay, so the reason why this is 3 is because it equals 1 only when x and y are 0, and then as x and y get bigger, it gets closer and closer to 0. The reason why this is number 1 is because it equals 1 whenever x or y equals 0. You see that? Whenever x or y equals 0, it equals 1. So you get this little ledge here along the x and y axis. This one has a vertical asymptote at the origin. So as x and y are getting closer and closer to 0, this goes down to negative infinity. These two are very similar. Let's do this one first. This one is this one. You can see along the x or y axis, it's going to equal 0. These two look similar, except if you look at this one, let's look at this one first. If y equals 0, you basically have cosine absolute value of x. So you can kind of see that. If you look along the x-axis, you are getting a cosine function. And if x is 0, you're getting y absolute, cosine absolute value of y, you're getting a cosine function there also. Whereas here, whenever x or y are 0, this equals 1. So that's why this is number 2. These, let's see. This is a contour map we were talking about earlier. They wanted to approximate f of negative 3, comma 3. So if you go negative 3 units to the left and 3 units up, we want to approximate that value. The z coordinate there is about 56, I think. Whereas 3, comma 2, 1, 2, 3, 3 comma negative 2 would be 1, 2, 3, negative 2. It's right about there. You get about 35. So what are we supposed to know about the graph of z, well, or f? It looks like there's a maximum somewhere here, and after that it goes down at about 0, 1/2. I'm not sure if that's 70, but it's around 70. And it looks like as you get as you're going down the negative y-axis, it's getting steeper, isn't it? Okay, a couple more. These are kind of hard to draw. This one isn't too bad. This one, it's going to be, I guess it's like 0. I didn't count, but it looks like it's about 0. It's getting bigger as you go out, but not quite as quickly. So it might look kind of like this. This one, I had a hard time with this one. This one along the y-axis, it's symmetric with respect to the y-axis, and as y gets bigger, it's getting more negative. So it looks kind of like that. Now they want you to draw a contour map. I chose this one. If x is bigger than, if x is if this is len y equals x, if x is greater than y, you're going to have hyperbolas along the x-axis, and if y is bigger than x, you're going to have hyperbolas along the x-axis. I think this is a hyperbolic paraboloid if you were to graph it. Okay, we're almost done. This is the last one here. Now we're talking about a function of 3 variables. You see, f of x, y, z. We don't know how to graph this because we don't have 4D-dimensional graph paper. But we can plot, instead of level curves, we can plot level surfaces. What does that mean? If you call this W, if we let W equal a constant, instead of having level curves, we have a level surface. So if you let W equal, like, say, 2 or whatever, this is a plane, right? If you let W equal a constant, you're going to have an ellipsoid. But if W equals 0, you're just going to have a point. And if W is less than 0, you don't have anything. Same idea here. If W is greater than 0, you're going to get the level surfaces are going to be paraboloids. If x, y, and 0 are 0, you have a point. Otherwise, you don't have anything if W is less than 0. This one's kind of tricky. The last one here. If W is greater than 0, I believe you have a hyperboloid of 2 sheets. You get hyperboloids of 2 sheets along the x-axis. If W equals 0, I believe you get a cone. And if W is less than 0, then you would multiply everything by -1, and you would have hyperboloids of 1 sheet along the x-axis. Alrighty, well, that's it. We'll talk to you later. Bye-bye.